Modern machine learning requires massive industrial scale to mimic human thought. Current artificial intelligence operates top-down as a statistical pattern matching engine. It studies vast amounts of text or images to predict the next word or pixel, generating results through correlation without semantic comprehension. Training GPT-4 on 13 trillion tokens consumed 1,287 megawatt-hours of electricity. Meanwhile, the human brain runs 86 billion neurons on roughly 20 watts. When pushed outside their specific training distribution, these models experience catastrophic forgetting. They remain structurally brittle. Synthetic intelligence offers a completely different path. Rather than extracting correlations, it replicates the bottom-up computational processes that drive actual biology. For decades, computer science has operated under brain chauvinism, the assumption that cognition requires a highly centralized nervous system. By looking past that assumption, we can build robust systems capable of energy efficiency while navigating completely novel environments. Biological systems actively operate as agential materials. Even without brains, cellular collectives act as competent, decentralized problem solvers. Researchers in synthetic biology can now create xenobots, kinematically replicating swarms of cells that navigate physical environments and sweep debris into organized, distinct piles. The primary obstacle for synthetic intelligence is the control problem. Standard top-down algorithms cannot reliably steer the emergent behaviors of these living systems. In traditional machine learning, engineers write explicit reward functions to guide a statistical model. Applying that level of micromanagement to a biological swarm fails. The physical environment is simply too dynamic. We have to stop dictating the movements of individual cells. Instead, we communicate using semantic, high-level goals. By building a semantic interface to program emergent AI-like behavior, we combine the communicative power of statistical AI with the decentralized capabilities of synthetic intelligence. Intelligence predates the existence of brains. Cellular collectives have been navigating anatomical morphospace, the mathematical space of possible physical forms, for millions of years. An axolotl provides a concrete biological baseline for this goal-directed behavior. If it loses a leg, local cells divide and rebuild it, dynamically reducing anatomical error until a perfect limb is restored. This diagram maps that anatomical morphospace. A cluster of data points shifts toward a central target, the anatomical set point. The cells operate within a cognitive light cone, coordinating to pursue a macro-level goal they individually cannot comprehend, mediated by bioelectricity. Biologists can exploit this cognitive glue. By providing a high-level bioelectric prompt, researchers can instruct frog cells to build a complete eye on the animal's flank without micromanaging the thousands of underlying genetic steps. Because biological materials inherently seek goals and respond to nudges, the next engineering challenge is computational. We need a translation layer that converts natural human intent into spatial biological interventions. The ZAP-GPT framework maps free-form natural language directly to spatial interventions, addressing the interface problem between human intent and decentralized behavior. This flowchart illustrates the prompt-to-intervention model. A text instruction, like form a cluster, flows into an SBERT encoder, which captures subtle phrasal nuances, separating commands to cluster and scatter. This embedding is projected through transposed convolutions, forming a two-dimensional spatial vector field. This vector field acts as an environmental nudge applied to a decentralized simulation of cells. It steers their collective movement while maintaining their local physics. The prompt-to-intervention model treats human language as a direct control layer for physical space, replacing rigid programming with abstract semantic constraints. Once the intervention is applied, the system must determine if the cells obeyed the text prompt without relying on brittle, handcrafted reward functions. This closed-loop diagram shows the evaluation step. A visual rendering of the cellular configuration and the user text prompt flow into a vision language model. It judges semantic alignment, how well the image matches the words, and outputs a scalar score, like 0.85. Cellular simulations are non-differentiable, therefore engineers cannot use standard backpropagation to train the model's weights. Instead, ZAP-GPT employs an evolution strategy. Over multiple generations, it iteratively mutates the prompt-to-intervention weights to maximize the semantic fitness score from the vision model. By removing engineered reward functions, the system develops an automated method for coordinating physical behavior through natural language. The system was trained on a single prompt, form a cluster, yet it reacted successfully to entirely unseen commands, including instructions to scatter. This generalization suggests the model's spatial outputs are linked to the meaning of the prompts. The swarm navigates a latent space of possibilities, responding to instructions that exist entirely outside the training set. This outcome aligns with the principles of motivated cognition. The system operates autonomously based on internal drives and physical constraints, guided by high-level nudges rather than deterministic scripts. Our formal models of Turing machines and rigid algorithms limit how we view intelligence. Those models are merely representations, not the absolute boundaries of the reality they describe. The physical interface, whether it is built from silicon, biological tissue, or a hybrid, is a vehicle for exploring structured, platonic patterns of form and behavior. The future of technology does not force a choice between artificial intelligence and biological engineering. The two disciplines are moving towards a synthbiosis. Statistical AI serves as the translational interface for the robust, agental hardware of synthetic intelligence.